All right, we have a pretty exciting lesson for us today because we are finally making the jump from vectors in 2 dimensions to vectors in 3 dimensions. And that was really the goal, right? We were trying to do a lot of stuff in 2 dimensions because it was easy to picture. But a lot of what we've done in 2 dimensions, we could have done without vectors in a sense. What we really needed to do was get a good handle on how vectors worked and some of the calculations that we could do so that we could move on and do calculations in 3 dimensions, or sometimes called 3 space. So today I think we're going to be okay trying to look at things mostly on just on the screen. It is going to be a little bit tricky for us this unit, and it is in general, so don't think that it's just because we're trying to do things online. Picturing things in 3 dimensions is hard, okay? And that has been true for all of the classes that came before you that had to sit in desks. It can be a difficult thing to picture, so we'll just try and get a handle on it. And we'll go slowly and sort of take it easy as we go. So first we're going to try and just define a point in 3-dimensional space. And what you need to notice is that's what your new grid looks like. That's how we draw it in 3 dimensions. And we're going to try not to do a lot of drawing. Okay, drawing things 3D is tough. So we're going to do it a little bit here just so you can sort of picture it. But most of the time I'm just going to say, okay, try and picture this in your head. And it's almost easier to picture it in your head than to try and draw it on paper. So the tricky part with what a 3-dimensional space or a 3-dimensional grid looks like, the x-axis is now pointing straight out of the page directly at you. And that's what that's trying to indicate in the picture on the left. So the x-axis is coming straight at you. The y-axis is now sort of this horizontal one straight across the page, and the z-axis is straight up and down on the page. So the x-axis is sort of the new one on there. The z-axis is where the y used to be. The y is where the x used to be. So we flip things around a little bit. But this is kind of the standard way of how we would draw a 3-dimensional grid. So if we start considering some points, the point 0, 6, 0, well, we're going to have an x coordinate, a y coordinate, and a z coordinate. Remember, I used the word coordinate there. This is a point again. Points had coordinates, vectors had components. So the point 0, 6, 0 would be 0 on the x-axis, 6 on the y-axis, and 0 on the z-axis. So that's around there. So we're going to say, where is it located? Well, it's exactly on the y-axis. The point 435, that becomes really difficult for us to draw, right? So I'm actually not even going to try and put a point on there. I don't think. This is one where I'm going to say try and picture it. 435, maybe I can draw it a little bit. 435 meant we came 4 out on the x-axis. Then we went 3 over on the y-axis. That was 4, that was 3. And then we went up 5 on the z-axis. So there's our point right there. And by drawing those lines in, we can picture it a little bit more. But imagine if I erased those blue arrows and just put a blue dot there. It's a 3-dimensional drawing that I'm drawing on a 2-dimensional piece of paper, right? You can't really get a sense of exactly where that point is. So the lines become crucial. We're going to see that again in a second. To describe where that is, well, that's kind of in the middle of nowhere, right? It's not on an axis. But what you might remember is we used to have quadrants. Right? We have our first, second, third, and fourth quadrant. And in this case, we don't have quadrants anymore. We have these sections. If you imagine how those axes would divide things up, think of them in as sort of cubes, right? Like a 2 by 2 by 2 cube. So that's divided things up into 8 different of these, I suppose, infinitely big cubes, right? They just keep on going. Well, we call those cubes octants. So we had our quadrants in 2 dimensions, we have octants in 3 dimensions. So for this one here, the way we could describe it, we could say it's the top front right octant. And that's something that we will hardly ever say ever again, because you say 4, 3, 5, and we're going to be able to picture where it is. Technically, that's the description, right? It's in the top, it's at the front, and it's on the right, and it's an octant. Okay. Again, we probably won't say that too often, but technically that's correct. The point C, 4 minus 7, 0. Well, I guess that's out 4 again. 4 this way, and then minus 7 on the y-axis is about there, and 0 on z, so we didn't go up and down at all. That point is no longer in an octant, right? It's not in one of those 4 particular quadrants. It's right on the borderline. So we say that's in a plane. The plane that it's in is the xy plane. So like we have a y-axis, an x-axis, a z-axis, this is called the xy plane. And the xy plane is just that. Well, imagine you were going to take a sheet of paper and lay it flat on the x-axis and the y-axis. That sheet of paper is the xy plane. And hopefully you can also picture the other planes. There's going to be the xz plane, and there's going to be the yz plane. The yz plane actually is the piece of paper, right, as it's laying on your desk right now. Okay, that's how we can describe some things. That's how we can sort of plot some points. Although, as I say, it's difficult to make them look real accurate. We can also define vectors in R3. So here's a vector, 5, 6, 3. Now the advantage of us doing vectors before is that all of the vectors that we'd previously done, we can take what we knew from before and still use it. So 5, 6, 3 is a vector that we're imagining starting at the origin and then going in a particular direction, 5, 6, 3. Now I've simplified the diagram a little bit. I haven't put the negative axes on just to make this diagram a little bit easier, because it says we want to try and draw vector v, which is 5, 6, 3. So we're going to attempt to draw it. By the way, we're going to draw this in that top front right octant. It's really tough to draw it anywhere else. It can be done, but it's hard enough as it is. We're going to just try and put it in that easiest quadrant where everything's positive. Okay, hopefully I can get this on the first try. It's not the easiest thing to do. 5, 6, 3. So we're coming out 5. I'm going to draw it fairly large, maybe come out to about there. So that was a distance of 5. And then 6 on the y-axis. Maybe to there-ish. This isn't going to look really good to scale, but that's okay. And then 3 up on the z-axis would look about like that. It's not bad. And that's where the end point would be of our vector. So the vector looks like that. Now the one thing that we often do to try and help make this 3 dimensions is we're going to take all of those red lines and I'm actually going to make it into a box. So I can kind of show you what I mean here. We've got that 6 on the front. I'm going to put another 6 here and connect like this. So I'm actually going to draw this 3-dimensional rectangular prism like that. And if you do that, the hope is that it gives you more of an impression that this thing is actually 3-dimensional. So there's our vector. Oh, I guess I can put vector v on there. Now, I want you to take a minute, pause the video even if you need to. I want you to try and calculate the magnitude of vector v for me. Okay, you did that on the first problem set. So you've already tried to calculate one of these in 3 dimensions. So see if you can do it again. And then unpause it, and I'm going to show you how I'm going to do it. Okay, so I'm now going to attempt to calculate the magnitude of vector v. But I imagine it's going to be pretty similar to the way you did it. I'm going to draw a line right there. And if I do that, that creates a little right angle triangle. I should call that something, shouldn't I? Let's call that, well, let's call it C, it's the hypotenuse. So if I do 5 squared plus 6 squared, that's going to give me C squared, right? Now, usually what we do is we square the 5, square the 6, add them together, take the square root. I'm not going to do that, though. Okay, I'll show you why. We've got this other side, which is our 3, I suppose, right? Well, our goal is to calculate the magnitude of vector v, which is our hypotenuse, right? I suppose I should put that on the other side if I can try and keep this looking the same. So Pythagorean theorem says there's this little right angle triangle there. So what I should do is I should go c squared plus the other side, which was 3 squared. Well, what's interesting then is that I can take the c squared back here, which I said I wasn't simplifying for, right? I'm going to substitute it right there. And so really what we've got is this three-dimensional version of the Pythagorean theorem. So the magnitude of v is equal to that, which I think I get square root of 70 for the magnitude of v. Okay, so the nice part, slide this out. Oh. In general, if you have some vector v, and those are the components, the way you calculate the magnitude every single time is just using that Pythagorean theorem trick. And it works in 3 dimensions, which is great. It makes it a lot easier. You don't have to do 2 calculations. You're just doing 1. So as I mentioned when we first started this lesson, a lot of the stuff that we do in 3 dimensions is going to be the same as what we did in 2 dimensions. And that's why we took all the time in 2 dimensions, right? Making sure that things were working out. Now we're in a pretty good shape. 3 most important unit vectors. Remember, a unit vector was a vector that had a magnitude of 1. So there are an infinite number of unit vectors, but these ones here were our important 3. You'll see them once in a while. Whenever we specifically refer to a vector I goes along the x-axis. It has components 1, 0, 0, and so it has a magnitude of 1. Vector j goes along the y-axis. These 2 we'd already seen, right? Vector j is 0, 1, 0. And our new one is vector k, and it has components 0, 0, 1. Those are important vectors. They're all unit vectors, as we said. None of them are collinear, which is helpful, right? They're all in 3 different directions, so that's going to be useful for us too. Well, if the vector rules that we had in 2 dimensions are the same as the vectors in 3 dimensions, the rules that is, then we should be able to do this relatively easily. If we want to do vector A plus vector B, it didn't matter that we've added in a 3rd component or not. The way you calculate vector A plus vector B is you just take the components and you add them up. So A1 plus B1, A2 plus B2, oops, not C, A3 plus B3. And just adding the components. Exactly, I think, what you would have predicted going in. Right? No surprises there. If you're subtracting the vectors, you subtract the components. There's a vector A minus vector B. K is a scalar. If we're going to multiply a vector by a scalar, which we're allowed to do, that's just K times that particular vector. So we can write it that way. And in turn, we can write it this way. Just expanding that scalar inside the bracket. We just did this one, the magnitude of vector A. And you're going to see it written more often like this, I suppose. We write vector A as A1, A2, A3. I could have written it as X1, Y1, Z1. That would have been okay. We tend to get away from that and use the A1, A2, A3 idea because technically, I mean, we're doing a lot of things now in 3 dimensions. I'm telling you right now, though, that the rules in 3 dimensions are the same as the rules in 2 dimensions. We can still picture things in 3D a little bit. There's no reason why we can't extend this to a 4th dimension or a 5th dimension or an nth dimension. It all applies. And that actually becomes a very significant problem in higher level mathematics, is looking at vectors with many, many components and trying to understand how they work. So all of these rules still work. You would just write vector A as A1, A2 up to whatever you needed. So that's why you're seeing this slightly different notation here. We'll probably use it more frequently as we go. A dot B, no, that's still the same. It's still magnitude of A, magnitude of B, cos theta. The angle in between is a little bit trickier to picture, so we'll have a tough time seeing that. But if you imagine just taking two pencils and pointing them off in any direction you want, there's an angle between them, right? No matter how you align them in three-dimensional space, there's still an angle there. That's the geometric way to calculate it. The Cartesian way is this. Again, just like we did in 2 dimensions. Projection. That was our slightly more miserable formula. It took a long time to figure it out at least, but the way you calculate it was just A dot B. Remember, this is the projection of A onto vector B. And I remember if it's onto B, that's what goes in the denominator, and that's what comes at the end. So the projection was A dot B over magnitude of B squared times vector B itself. So we end up with a vector answer. I don't think any of those rules really changed, right? Everything there is the same as what we had done before. So no surprises there. Determine the value of k such that the vectors are perpendicular. So we're given two vectors, and we want vector x to be perpendicular to vector y. By the way, I can't remember if this is going to come up in the homework tonight. It's going to come up at some point. The word perpendicular is the same as the word orthogonal. And I remember it's going to come up at some point. I can't remember when. It's going to say it's going to ask almost the exact same question. Determine the value of k such that the vectors are orthogonal. Orthogonal and perpendicular are the same word. Okay, orthogonal is a fancier word. If we want x and y to be perpendicular, what we know is, well, it means the angle has to be 90 degrees. And that happens, if that happens, then the dot product has to be 0. And so our dot product is coming in handy again. We're able to use it quite a bit. Dot product is nice and easy to calculate in Cartesian form here. We just do 3 times 4, 5 times k, and then minus 2 times 7. And we know the answer has to be 0. And now, really, this is just it's a fancy way of us creating an equation, right? This is probably it's a pretty easy equation compared to what you guys are used to. The value of k is 2 over 5. So fairly simple solution, but a really good use of the dot product. Trying to find two vectors that are perpendicular to each other, and we're just making use of the dot product to actually figure out what those vectors should be. Okay, one more for us. Again, all we're doing is we're just practicing a little bit, trying to do some of the calculations in 3 dimensions. Consider the points A, B, and C. Determine the projection of x onto y if vector x is AB and vector y is AC. So this is an important one to bring up because I've given you 3 points. And your textbook's done that a few times with homework questions where they give you points and not vectors. And you have to be really careful. I mean, they're good about it. They say points. They use round brackets instead of square brackets. But it's very tempting sometimes to just look at that and think vector when in fact that's not the information that they're giving you. So we need to figure out what vector x actually is. And vector x is from A to B. And I'm not sure if you remember, a few lessons ago we talked about how there were 2 different ways of doing this. The way I often like doing it is I just like thinking about how we go from one vector to another. So to go from 5 to 2, I had to subtract 3. To go from minus 2 to 1, I had to add 3. And to go from 3 to minus 1, I had to subtract 4. And that's the way I like to think of it. The other way to think of it was you take the second point and you subtract the first point. So you would have gone 2 take away 5, which is minus 3. 1 take away negative 2, which is 3. And minus 1 take away 3, which would give you the minus 4. Both ways absolutely correct. It just depends on how you want to think of it. Vector y is a to c. So from 5 to 6 would be a 1. From minus 2 to 0 would be a 2. And to go from 3 to 2, you'd have to take away 1. So there's our two vectors, x and y. So we needed that before we could do anything. How do we calculate the projection of x onto y? Well, our formula was dot product on the top, magnitude of the vector squared on the bottom, and that's the vector that we're projecting onto, and then times that by vector y. So we're going to do some more work on the side. This is the way I like to do it anyway. We need to calculate the dot product, and we need to calculate that magnitude. So the dot product would be minus 3 times 1 so we just get a 7. Yep, I think that's okay. This is tougher, by the way. I don't have anyone behind me going, hey, you got that wrong. So I actually have to make sure that I'm doing things right. I hope I'm doing okay. Usually I'm good for a bunch of screw-ups every time I teach one of these lessons, so fingers crossed. We have to do the magnitude of vector y. I guess we have to do magnitude of vector y squared, all right? So I'm almost going to write this out in a silly way to start. The way you calculate the magnitude is you do each component squared, right? And then take the square root of it. But I wanted the magnitude squared. So what happens is that squared on the outside cancels with that whole square root. We're left with 1, 4, and 1, so that's just 6. So it turns out nice, right? I mean, it's nice for the projection that we're squaring that magnitude because it gets rid of the square root for us. Okay, all the work's done on the side. Back to the projection. I'm just going to slide over a little bit so I have more space. 7 on the top. Again, fingers crossed I did all those calculations right. 7 over 6 times vector y, which we should simplify a little bit. That's 7 over 6 times 1, 2, minus 1. And then we'll go ahead and multiply that through the bracket. Multiplying by 1s is easy. If you multiply it by the 2 is going to simplify with, whoops. Oh, no, that's right, sorry. Simplify with the denominator a little bit. So we get 7 over 3, and then minus 7 over 6. That's our projection. So there's more to it, right? To do a projection, you have to do all those. Well, you definitely had to do the red calculations on the side. The fact that I gave you points instead of vectors meant you had to figure out x and y first. So a projection calculation is certainly a little bit more difficult than some of the other ones. One example that we didn't do, we did the other day in 2 dimensions, we didn't do it in 3 dimensions, was calculating the angle in between vectors. We do that the same way, right? We did that all with the dot product. So we can do those questions in exactly the same way as we did in 2 dimensions. So if you see that one come up, you know how to do it. You'll be fine there.